Yeah.
Okay, I thank you for this nice school conference. Thank you for the opportunity to talk. I will talk about my work with Roma Gonin, who is not here, but who could be here at any point. This is about representation theory of toroidal algebra, and this is related to the subject of the all lecture courses, and I will point to where I see some links, but mainly the talk will be independent. I just try to explain what we are doing. And of course, I encourage you to ask questions at any point. Okay, so the subject is some representation of toroidal algebra, and toroidal algebra is quite non-trivial object, and and I want to start rather slowly, first explaining what is toroidal algebra and how it comes. And I mean, for me, the most natural point to start is a McDonald operator. So McDonald operators are different operators. So they're different. So the basic different operator I denote by T here. T, it is shifted by Q. Its argument now here variable xi. And McDonald operators, they are labeled by the integer r, which can be any number from 1 to n, and it acts on the space of functions on n variables, and is given by the following formula. So we have a summation of all subsets of the size r. For this subset, we have the difference operator for the r, if you want. So it shifts r exactly as variables which belong to this subset, with some rational functions, where we have products over I and j, where I belongs to set I and j does not belong to set. So this is a Q difference operator, and it also depends on some additional parameter t. For t equal 1, this factor cancels, and we get just sum of different operators over all subset of size r. Okay, so this operator acts on the space of functions on n variables. But it appears that it acts on the space of symmetric polynomials. So this is some sort of lemma. It's not absolutely obvious, because if you look at the formula, then in principle we could have denominators. But it is quite easy to argue that if you start from symmetric polynomial, then we obtain symmetric function, and this symmetric function cannot have poles of first order. So after this whole summation, we obtain indeed polynomial, not rational functions. And if you look at the polynomial of these variables, this operator clearly preserves degree. So if we fix some degree, we come to some finite dimensional operator. And it's natural to ask about its diagonalization, its eigenvalues, like in standard quantum integral system story. And its eigenvalues are famous Macdonald polynomials. So here, for the beginning, I defined Macdonald polynomials, which are symmetric polynomials of n capital variables. It is well known that the basis and the space of symmetric polynomials are labeled by Young diagrams, by partitions, and Macdonald polynomials are also labeled by partitions. This formula is a bit implicit formula, says that these Macdonald polynomials are eigen vectors of the Macdonald difference operators. And the eigenvalues can be written very explicitly in terms of the diagram lambda, but I will not use this formula, so I just wrote them by some e. There is a formula. This one of the definition of Macdonald polynomials. One of the very first remarkable properties of them that the the base of the matrix which transforms other known bases, and for example, monomial basis of symmetric functions to the base of Macdonald polynomials is triangular. So Macdonald polynomial P lambda is equal to m lambda plus sum of here we have summation of a partition which are less than lambda in the dominant order with some coefficients. And the same triangularity property holds for Schur bases and actually for many other bases. Another remarkable property of Macdonald polynomials is that in the limit where n goes to infinity, this Macdonald polynomial stabilize. So if we take the decompositions, for example, monomial basis, then if we take the limit, then this coefficient stabilize. They do not depend on n for n sufficiently larger than the number of boxes in the partition lambda, if you want, in the diagram. So if we limit of m lambda and mu are monomial symmetric functions, so we can define by this formula limit of the Macdonald polynomial, and this is Macdonald symmetric function. Any questions? Should I resend my slides to the chat again? Okay.
That would be nice, by the way, because I just arrived. Sorry. Sorry.
I can resend them again, and you will decide whether it's necessary to listen.
Sure.
Okay. Okay, they say they're quite large. Sorry. Okay. Okay. The algebraic structure which we have, in which the Macdonald polynomials appears quite natural, is a famous Cherednik double affine Heke algebra. Let me recall the definition of the Heke algebra. So the standard Heke algebra is the algebra which is generated by T1 and so on, Tn minus 1. Today I talk only about type A. So this is a Heke finds Heke algebra which correspond to An minus 1 or SLN if you want. And this T1, Tn minus 1, they should satisfy standard braid relations. So neighbors. For neighbors, we have these braid relations, and if I and j are distant, so if absolute value of I and j is greater than 1, the corresponding generators commute, and they should satisfy quadratic relations, which is written here. For as usual, for v equal 1, this relation means that any t is an involution, and we get the relations in the group algebra of the symmetric group, and this is a deformation. This Heke algebra and double, I skip just affine Heke algebra and define double affine Heke algebra. As a vector space, it is a standard Heke algebra multiplied by two algebras of Laurent polynomials. We have two additional sets of the commuting variables. We have which are denoted by x's and y's. So x's commutes with itself, y's commutes with itself. Relationship between Heke algebra and x's is given by this. The only trivial relation is this one. Again, if j is different from xi and xi plus 1, then tj commutes with xi. So the only trivial relation is this one. For y's, we have similar relation. The only slight difference that here we have inverse power compared to this. And in relations between x's and y's, we somehow came to the finite Heke algebra. This is some sort of triangular decomposition, similar to what we have in for simple Lie algebras, so somehow similar. Here I wrote one relation which is actually sufficient to impose. All others are corollaries. And this relation is that some sort of the commutators of y2 and x1 is equal to 1 squared. And also I want to stress that in this double affine Heke algebra, we have one more parameter. We already have parameter which is denoted by v, which appears in the Heke algebra relations. But we also have parameter which is denoted by q, and this appears in q commutator. It appears that certain generators here and here q commute. Namely, if we take product of all x's, it will q commute with any y. And if we take product of all y's, it will q commute with any x. To be more precise, a double affine Heke algebra is defined for any root system, fine root system, maybe better to say, and so on. So this is a definition of the double affine Heke algebra for GLN. So this is, for some reason, this is a bit bigger than double affine Heke algebra for SLN, for AM case, but I try to write down it explicitly, so maybe it's not. If you have any questions, please feel free to interrupt. This algebra has the famous polynomial or чередник representation. It acts on the space of the Laurent polynomials on this axis, x1 and so on, xn minus 1. Where x is x by just multiplications, and y's are some sort of different separators, which could be called Dunkel operators if you want. And y's are commute, so y's form some sort of integrable system. One can ask what happens if we try to diagonalize y's, and the answer is we'll get Macdonald polynomials, but now we have they will be non-symmetric because we do not impose any symmetry on x. But we can symmetrize. So we can usually people just take symmetrizer on the Heke algebra. For my own reasons, I pick antisymmetrizer. This is not big deal. So this S minus is antisymmetrizer. I wrote it V antisymmetrizer because we have V in the relation of the Heke algebra. And if we act on this antisymmetric part, we get from this commutative algebra, we get a Macdonald commutative algebra, and the eigenvector will be Macdonald symmetric functions. Here I wrote some relations of parameters, so I use V, and this V squared is T over Q, where T and Q are standard parameters for Macdonald theory. Okay. Okay. So here I just I recall the Macdonald polynomials, Macdonald operator, and double affine Heke algebra, and this is one of the way to come to the to toroidal algebra, which was in the title of my talk. So on the space of the symmetric polynomials, so not Heke algebra, but it's spherical subalgebra acts. So this S minus Hn is an algebra which consists of elements of the form S minus X S minus, where X is any element of the Heke algebra. This is again unitary algebra where unit is S minus. Unit, and it acts on the space. And there is I think observation, not due to Chutnik, but due to more recent papers by Schiffman and Vesero, that this algebra can have presentation in terms of this algebra acts on the symmetric functions. It's natural to ask what is the presentation of this algebra in terms of generators and relations. And so in case of finite number of variables, so it appears that double affine Heke algebra has more simple presentations than its spherical part. one of the way to present the spherical part in terms of generator relations is to introduce infinitely number of generators, which are denoted by PAB, which has some sense degree A on x's and degree B on y's. So morally, up to some simple shifts and so on, they are just symmetrizers of the following elements: x1 in power A, y1 in power B. So I use morally because here I just wrote x in power A, y in power B, but actually I should write them in some clever order to be, in order to have this formula just literally correct. And also I probably should put here some number, some q number. But if we are not too honest, then if you want to have an idea what are these generators, this and so this generator has degrees A and B, and x degree and y degree. And another observation due to Schiffman zero that if we take a limit n goes infinity, then there is a limit of the set of generators, and this limit is actually one of the definitions of the quantum toroidal algebra. Maybe I lost one of the dots. I put it again. Here is some pictures. So we have generators which are labeled by two integers numbers, and so I represent them by dots on this diagram. After this limit, we also will have two additional generators which are denoted by C and C prime, which are central and lives in the zero. And the relations are as follows: so C and C prime and central. And another relation, I will not write full list of relations. It is not necessary for this talk. That for any line which we have here, I draw 4 lines. I don't know whether you see my colors. I suppose this is line is green. This is some sort of purple. This is red. This is yellow, maybe orange. But okay, so if you see my lines and my pointer, then maybe you understand what I'm saying, that for each line we have Heisenberg algebra with the central element, which is some product of C and C. So before, for example, for this line, we have this line correspond to elements of the form P0B. So this is will be symmetrization of y's, y in some power. And y is commute, so in the limit, this line should, first glance, should give commutative algebra, but there is a central extension, and in the center, this central extension, we get the Heisenberg algebra, which corresponds to this line. And actually, we can have Heisenberg algebra, which corresponds to any of this line. Of course, there's not full list of relations. There is. One can also write a commutational relation between elements which correspond to different lines. This can be done. I maybe don't want to do it on the talk. I want to add that there is a huge symmetry of this algebra, namely there is an action of the group SL2Z. This is not surprising. If you know about Heke algebras, double fine Heke algebras, they also have the SL2Z symmetry, and the spherical part has SL2Z symmetry, and the symmetry survives after the limit n goes to infinity. So we have a SL2Z limit on the toroidal algebra. The name is quantum toroidal GL1 algebra. The resonance name is the following. We have we can think that we have GL1, we have one generator, and now we can think that we have currents in two variables, say, I don't know, Z and W. So we have P of Z and W, which is expanded and as a Laurent polynomial in Z and W. So we have infinitely many generators labeled by mods in Z and W. So this is what we have here. We have generators labeled by two integers. Any questions? Okay. If no questions, let me say a few more words about this toroidal algebra. There are different approaches. So I defined this it here similar to the work of Schiffmann-Vasserot. Another approach is look at this algebra as a quantum group. So we can take certain. So here we have many generators. This is in spirit like Cartan-Weil generators, so, and so on. But there is we can restrict to the first three columns. So this is column number 0, P0. I don't know, for some reason A. I don't know. Here we have P. This is the first column. This is the minus first column. And these generators can be viewed as generators of the Chevalier generators, or generators in the current realization, like U-Drinfeld realization. And one can write relations which are very similar to U-Drinfeld realization of this L2, quantum fineness L2. The main difference is that now we have two parameters, Q and V or Q and T, whatever. And, therefore, they be, how to say, this is some sort of next example. We have SL2, and next example is this quantum toroidal algebra. And one more advantage of this presentation is that now this algebra, in this, after writing this new Drinfeld type presentation, we can write a coproduct. Like a new Drinfeld coproduct and new Drinfeld realization. Approximately, this coproduct looks like this. The coproduct of E of Z is E times K plus 1 times E. And coproduct of K plus is like group element. Coproduct of K plus is K plus times K plus. Okay. In this presentation, maybe this algebra appeared actually first in the papers of Miki, which somehow followed the paper by Dingy-Ohara. So another name of this algebra is quite common, more physical literatures, Dingy-Ohara-Miki algebra. And this algebra has very deep relation to W algebras, which will maybe appear in the Flux talk of today by Heke. Maybe no, I don't know. And the relation is as follows. So as we said, this algebra has a representation of the space of symmetric functions, and then more. And this representation, I defined it as a limit of something. So and of the representation of the spherical in space of finite symmetric function, finite number of variables. But in the limit, after the limit, something simplifies. And for example, we have more explicit way to write down this representation, and this way is due to Bosonization. We can realize the space of symmetric functions as a space of polynomials on the pKs. And we have additional operator section here is a differentiation with respect to pKs. pKs is a Newton power sums. And then this red generators will be just pKs and differentiation. Here tilde means that there could be some factor here which I ignore. And the E of Z and F of Z are just some exponents of the pK, some vertex operators. Exponents of the pK due. And this formula was written by Heke and Sharishi some time ago, more or less independently on other approach to this algebra. This also gives some sort of Bosonization of the McDonald operator. So McDonald operator from which we started is a zero mode of this E of Z. Implicitly, this can be written by this form. Now, if you take this is This is the formulas for the action of the toroidal algebra in space of symmetric functions. As I said, this algebra is quantum group, so we can take tensor product of such representations, say M representations. So we get an action of the toroidal algebra on the space of tensor product. So in this space, we have not one Heisenberg algebra PK over D over PK, but M copies of the Heisenberg algebra.
Can I just ask? Sorry, something happened. Oh,
Any question is welcome.
So, Misha, these Reshotka symbols in the definition of EZ and FZ, they represent some numbers, do they?
Yes.
But you just didn't specify them.
Yes, they are very explicit,
Yeah,
but
you, I just don't understand. Yeah, okay, understand.
But I just want to ignore them. Yes. So we have, if we take tensor product, then so we have it can be shown that the image of this algebra on the tensor product is a W algebra, Q-deformed W algebra for GLM. And again, if we take limit M to infinity of this W algebras, we obtain this toroidal algebra. There is, so what I said that there is some big algebra, toroidal algebra, which is some sort of quantum group. And one can think of that as a limit of the spherical Heke algebras. Or if you are more familiar with the W algebra, then this is a limit of the W algebras, where again rank goes to infinity. Here I'm a bit sloppy. This limits of the Heke of the spherical Heke algebra, and limits of the double algebra, they should be viewed in somehow in different sense and so on. There's some difference in completions, but morally, I think what I said is correct. There's some big quantum group which appears as a limit either from this construction, either from this construction. It depends on your taste. Which algebraic construction do you prefer to start with? Okay, I pause for the questions. Okay, there is no questions. Oh, I just don't hear him and don't see them in the chat. So okay, and what this algebra is very interesting, also due to its geometric interpretation. And it appears in the models at the same time. Of course, I can't explain full history here, so just in words. So if the manifolds, which are important for the story, are the modular space of the instant instanton of C2, or if you want framed free sheaves on C2. So the R is the rank and N is the second Chern number. This is some sort of abstract definition. It has very concrete descriptions in terms of ADHM, or if you want this, if you prefer this Nakajima-Quiver variety. For very simple quiver, which is just one loop. The simplest example where R is equal to 1, then the spaces are just Hilbert scheme of points on C2, and number of points. And there is a theorem the key names I think here, that this toroidal algebra naturally acts via some geometric correspondence on the equivariant K theory of this modular space of these two parameters Q and T, on which this algebra depends, are just equivariant parameters. So we have action of the two-dimensional torus on C2 to promote to the action of the moduli space of instantons. So in respect to this action, we take equivalent key theory, and these are Q parameters here. And actually in this way, so as I said, here at this point, we just obtained some representation of this toroidal algebra, but actually it was the same representations we had before. So for R equal 1, where we have just a Hilbert scheme of points. In this way, we obtain the representation in terms of symmetric functions. And if R will be larger, we obtain the tensor product of R such representation. On this space, we have McDonald operator, and geometrically, it is a tensor product with tautological bundle, which we have on the MRM. And natural basis, which eigenvalues of the McDonald operator, G, let me know by G lambda integral McDonald polynomials. It correspond to the classes of the fixed points, torus fixed points on this model space of instant. And in this case, just Hilbert schema. Of course, it is well known that this basis is parameterized by partitions, so we have identification. In some sense, this is an analog of the Gelfand settling basis, which is also a base of some integrable system, and many formals in the Gelfand settling basis have some factorized form due to the geometric origin of the Gelfand settling basis. This is an analog of the Gelfand settling basis. Okay, this was a very general introduction to toroidal algebra, but now from the geometry, we know that there are more bases. We know, because we know, I mean that this is due to Konьков, Maulik, Konькov, where they defined stable envelope bases. So Maulik, Konькov is paper about cohomology, Aganadzich, Konькov about elliptic case, and somehow in the between of them we have stable envelope basis in key theory. And this basis now depends on some additional parameter, which is some bundle and so on, but in our case it will be just integer, real number. And this basis actually has some sort of the chamber structure. So it actually depends on, so we have a basis which depends on some continuous parameter, which is denoted by L, but it changes where L goes through rational numbers. And if we look to the basis for Hilp N capital, then something changes only if the denominator of this rational number is less than this N capital. So for any fixed number of points, we have countable many bases which are can be labeled, for example, by integer numbers. And this for I didn't give you the precise definition, but just some pieces of definition as follows. So first of all, this basis is triangle with respect to McDonald basis. It is convenient to change normalization. So instead of the p lambda, which instead of g lambda, which I used on the previous slide, which is an integral normalization, and p lambda, which is a normalization which starts from which is convenient for monomial normalization, I introduced one more normalization, m lambda, which is somehow inverse to integral normalization. So in G we have the coefficients don't have denominators, and here we have many denominators. Lambda are actually rational. Anyway, so for triangular properties, this is not important. So we have it. First of all, we have triangular property. This is base triangle with respect to McDonald basis. another property is that this base is integral. So in terms of symmetric functions, it means that if we decompose this base in Schur bases, then the coefficients are Laurent polynomials, not rational functions, with integral coefficients. And there is a very important window conditions which says that the degrees of these polynomials satisfy certain inequalities. If time permits, and there's no questions, I hope it will actually permit, I will show you some examples of this window conditions later, but now I'll go. So, I mean, what to take away is that there are, in the space of symmetric functions, we have standard Schur monomial basis, we have McDonald basis also, but there is a certain basis which, at least formally in the definition, depends on the real parameter, but actually has chambered structure, so depends on the rational, something important happens on the rational numbers, which has geometric definition and combinatorially is defined by this property. Just to have some ideas of the first simplest example is where this rational number is equal to 0, then this base is just Schur polynomial. Then if we shift this parameter by 1, then this is equivalent to the action of the Garcia-Hyman operator Nabla, which is like McDonald operator, but not precisely. So this is another operator which acts diagonally on McDonald basis with some functions, which are more or less product of the contents of the boxes in the diagram with normalization. And it follows from this property, then if this L goes to infinity, so we apply infinity many times this Nabla, then instead of Schur polynomials, we get McDonald polynomials. Maybe curious to know that for P lambda, integrality property breaks. So this is not part of the, this is not terrible. Anyway. Okay, so with this definition which comes from geometry, or if you want, it can be stated combinatorially, but what it means in terms of representation theory? Do we know this basis from the representation theory of the toroidal algebra? And actually, this is the subject of our work, but before explaining our result, I state the conjecture of Gorski-Negut, which actually motivated us. And the conjecture said that this base has a representation theory interpretation, but in some dual setting. So these bases are natural not maybe from the point of view of the toroidal algebra, but from the point of view of another algebra, which is quantum affine GLN. Before we had toroidal GL1 algebra. And now somehow unexpectedly, and I think it was unexpected at the time, absolutely, that another algebra comes to the play, and appearance of two algebras should be viewed as some sort of duality. In this case, GL1, GLN duality. So there is an action of the algebra of the quantum affine GLN. Its quantum parameters V is related to McDonald parameter by the same formula Q over T, such that this S lambda, the stable angle base, is so-called standard basis in the Fock representation of this GLN. And I will recall this definition of the standard basis, but now maybe you can believe me that there is some definition in the theory. And this conjecture was supported by, of course, by checks on the first levels. I forgot up to which one. So they have quite trivial examples. And also they had some, they proved some sort of particular case. They proved that Heisenberg algebra in this quantum affine GLN, actions of Heisenberg algebra on the standard basis is actually coincide with the action of the this rotated Heisenberg algebra in toroidal algebra on the stable envelope base. So from the point of view of toroidal algebra, this leads to some SL to Z transformation. When we defined it usually in the standard generator, which correspond to these three lines. But it appears that for this stable envelope base, this is more natural to rotate our head, our point of view on this toroidal algebra, and mainly concentrate on the. So, and after this rotation, this natural Heisenberg will be this rotated. But it is a completely non-trivial operations. I said there is an action of cell to Z by automorphism, but this is like Lustig's group, braid group action of the quantum group. This is non-trivial group. For example, the original interpretation is irreducible with respect to standard Heisenberg, but absolutely not irreducible with respect to this rotated Heisenberg algebra. And of course, this is clear that Fock model is not reducible with respect to Heisenberg in the quantum affine GLN. You need quantum affine SLN also. And this quantum affine SLN remains unstudied algebraically. This conjecture was proven by 1 year ago in paper by Yasha Kononov and Andrei Smirnov using some geometric approach, some 3D mirror symmetry. I will not talk about it at all. And as I said, this conjecture, this result is some sort of duality. So we explained some basis for the G1 toroidal algebra using another dual algebra, which is a quantum affine. Questions? Okay. Now let me state the theorem which we have. The theorem is following. So we somehow reverse the logic. We start from the quantum affine GLN and then reconstruct the toroidal algebra. But this, in order to do such construction, we need not just quantum affine, but some additional data, some additional operators, namely so-called vertex operators. So let us take a basic representation of the affine GLN by pi m. I don't know, pi m it's highest weight. Fm is the corresponding Fock model. We have vertex operator which maps from Fm to Fm of this form. So V is the standard vector representation of the quantum affine GLN, and these are the vertex operators. So I didn't write names here, but yeah, let me add them. So the names here could be Jimba Miva, Kayama. Jimba Miva studied for such vertex operator for SL2, Kayama for GLN. But of course, actually, before they appeared in the definition of the QKZ equation, so the reference would be Frenkel-Stich. Frenkel-Stich for general reference for any level and so on. Here, this is a basic representation, so level 1 representation. And the fact that we have two types of representation, so left and right. We can multiply on vector representation on the left or on the right. This is due to the fact that we have now in the quantum group, so when the product is not co-commutative. And dual, so we multiply on the source or on the target. This difference between phi and phi. So anyway, so using this vertex operator, we can actually construct action of the quantum toroidal algebra G1 on this Fock module, where the Heisenberg is a Heisenberg of the quantum affine algebra, as actually suggested by Negod's formulas, and the E of Z and F of the Chevalier generator are a combination of the vertex operator. And this is rotated Fock module. So this P's are the rotated Heisenberg, and E and F are next columns. Maybe I should change the colors here. Let me do this. So this is F. This is, I think, E. Here, similar here. This is F. This is E. And so these two lines, they are parallel to the red lines and neighbors. Neighbor in this integral lattice. And so the A means that this actually this formula satisfies the relation of the quantum toroidal algebra. The corresponding module is a twisted Fock module, and the natural basis, which we had here, standard basis, so is integral and triangular. So here means that it satisfies first two properties of the stable envelope basis. And actually, conjecture it also satisfies this window condition in agreement with Gorski-Negot conjecture and Konop's theorem, but we didn't prove this yet. Conjecture, we checked some properties like this in cases and so on, but this is still a conjecture. Okay, maybe I skip about deformed transfer algebra and just explain you something about the proof and some why do we come to this. And so as I said, algebraically our idea is this is some sort of duality between toroidal and between GL1 and GLN. On one side we have quantum toroidal, on the other side we have quantum affine, but this is just a matter of the statements. It is believed that actually on the both sides we should have toroidal algebra. And our first idea is a finitization of all this story. And this is quite natural from the definition of the stable envelope basis and so on. By word finitization, I mean the following. So the standard Fock module of the quantum affine algebra has semi-infinite construction. So you start with a tensor product of n capital vector representations, and then apply Antisymmetrizer, and then take the limit n goes to infinity. Since the Fock module has this construction, then it is natural to expect that similar duality and so on should valid even before the limit and even before Antisymmetrizer. And this is actually our first step. So we take the tensor product of n vector representation of the quantum affine algebra. And there is a well-known fact that there is a Q affine version of the Schur-Weyl duality. So in this space, there is an action of the affine Heke algebra, where morally T goes X by just finite matrices, and Y's X just by Y's since this evaluation, this vector representation. And this is well known. references are Cherry Presley, Ginsburg, Vasirot, and actually Cherednik. There's some formulas can be found in the paper by Cherednik. And our first theorem that this HV can be this finite Heke algebra can be naturally promoted to the double affine Heke algebra. And why it is natural? Because there is a statement by Schiffman-Vasirot that there is from which I started, the spherical Heke algebra is the toroidal algebra is the limit of the spherical Heke algebra. In particular, there is a map from the toroidal algebra to spherical Heke algebra. So if we promote this algebra to the Daha, and then we get spherical Daha, so we somehow get the toroidal algebra acting on here. And then it remains to take the limit. So we want to have some space in which we have action of two algebras. We construct the space is constructed as a limit of the wedges. So we come before we take not limit but finite tensor product, and even before taking the wedge, we obtain something which in the limit will give us toroidal algebra. This is the formulas for these extensions are very explicit, and I still somehow suspect that this theorem can be found somewhere in the literature or something close. So we more or less we take so this combination of two formulas. So if n is equal to 1, then these TIs are just like these and so on, and we get this is a standard Cherednik representation. If so, in order to reconstruct X, we take the formula from the standard Cherednik representation, but T and Y's are taken from the Schur-Weil duality. So combining this Cherednik formula and the Schur-Weil duality formulas, we obtain this our representation. This representation, it is now known that depends on some additional number which I denote by n prime, and its meaning is a can be seen as a degrees. So this is why. Okay, I wrote down the formulas somehow explicitly here. So I denote the natural basis in this vector representation by EI, where I runs through all integers numbers, assuming this periodicity. If you act by Y, then the index should by M. Space, we have two operators, kappa and D. Kappa shifting index by 1, D is a difference operator with respect to Y's. And the operator X is written by standard form in terms of the pi, and pi is up to some permutation is a Q difference operator. So we take D, apply D, and then apply kappa in power and prime. So we take Q difference operator and then shift degree. So in particular, our generators now have the following degrees. Degree of any xi is equal to n prime, and degree of y is equal to n. So this representation is somehow twisted representation of the, and this is actually one of the theorems, that this representation is a SL2Z twisted Cherednik representation of the Daha. Okay, this lemma is kept here mainly for motivation, and here I said that actually on this case of the polynomial, non-symmetric polynomials, finitely many variables, we can actually have this stable envelope, some spirit of this stable envelope constructions, and I don't know, maybe it should be proven geometrically or so. Let me do digressions and say, give you example of the window condition. the most trivial property here. The window condition is given in terms of degrees, upper degree and lower degree, and this degree is computed for the Laurent polynomials. So the upper degree is a degree of the lowest term. So, for example, for this polynomial it will be -2, and low degree for this polynomial is 1. Now, in symmetric case, which is part of the original Gorski-Negut conjecture, we have to introduce normalized Macdonald polynomials. In simplest case, where the slope is equal to 0, stable on basis, the sure polynomial basis, we have the following formula of the transition matrix. This is because I write this formula, I put concrete degree, so I have symmetric function of degree 3. And we compute this upper low degrees, and what do we see? We see that of course I can write matrices upper triangular, because here we have zeros. And the window condition means the following, that on this matrix we have zeros only on the diagonal, and in this matrix in each column the maximum number is on the diagonal. So the 6 is greater than 5 and 4, 5 is greater than 4, and so on. Okay. And in non-symmetric case, and this is, I mean, this what we did by calculations, but so if we take this example of the now, because we have finitely many variables, I have to specify not just degree but also number of variables. And maybe the largest example which you can write on the slide is that we have 3 variables in degree 2. So in this case, we have 6 composition. So it is if we speak about polynomials, and the matrix here wrote the matrix difference has the following form. And again, we see the same properties. The maximum number in each column, the maximum number is on the diagonal. This 5 is greater than all these numbers. This 4 is greater than number. So this is this magic window condition, which actually I don't have any deep understanding. So wide confidence theory symmetric function, even for sure polynomials. So for sure polynomials and their decomposition with respect to this Macdonald basis, it can be proven, but the proof which I know is not explanation. I hope there is a much better proof which explains this window condition better, but I don't know. Okay, anyway, so let me return to the ideas of our proof. Here I stated that we constructed action of 2 algebras on this space. So we promoted the quantum affine algebra to toroidal algebra. We promoted affine Heke algebra, double affine Heke algebra. Now we apply Antisymmetrizer. Okay, let me write this here. So the I denote by lambda the basis which will be which later will become a standard basis is Antisymmetrizer applying to some standard means lambda 1 tensor. So we take the decomposable tensor and then antisymmetrize it. Of course, this is minus of this antisymmetrizer is the Heke algebra, so this formula depends on V. And such vectors lambda they form a basis in n tensor power, and I denote this n tensor power as wedge. And in order to write down formulas and deal with all this, it is convenient to introduce vertex operators. What do I mean in this verse, vertex operators? So maybe two properties. First, that all these vertex operators, phi star, psi star, they all are intertwiners for the quantum affine algebra. Okay, and property B, which let me state it for at least for phi, that phi is the sum of the its mods, phi j mod j, and each mod phi j acting on lambda is ej, which lambda, or in other words, is S minus of ej tensor e minus lambda 1 . So this is just standard operators, deformation of the standard operator on the wedge power. So we can either multiply by some ej, or of course phi star is differentiation with respect to ej, and psi apply corresponding multiplication differentiation on the right. So these are quite natural operators, and they're studied. So what is the reference? Okay, let me mention two papers. Kashivara, Miva Stern is one, and on the other hand, let me mention paper by Leclerc at Thibault. Yes, I want to check my spelling. Yes, I think this is okay. So such papers in the middle of 90s, the operators were introduced, and it appears that if you look at this, the corresponding operators act on the V wedge space, then the action of the toroidal algebra, action of the spherical Heke algebra, is naturally written in their terms. So E of Z is just psi phi star, and F of Z is phi psi star. And so we have two steps. Over better 3 steps. So on the first step, we take non-symmetric finite number of polynomials and symmetric finite number of variables and introduce action of the DAG. Then we symmetrize, or technically we antisymmetrize this space and consider action of the spherical Heke algebra, which is actually the certain quotient of the quantum toroidal algebra. And then we should take n limit n goes to infinity. And in the limit, just in Bertrand, we take this space and take the limit n goes to infinity. And this, on this space, we have two actions: action of the quantum affine algebra and action of the toroidal algebra. And it appears that as a representation quantum affine algebra, it goes to basic representation. And this is actually shown by the papers by Leclerc, Thibon, Kashvarmiev, Stern, and so on. And our result that we observe that in the limit where n goes infinity as a representation of toroidal algebra, we get twisted Fock model. In this way, we obtain on the same space action of two algebras commuting. And this limit appears to be quite tricky. It sometimes happens that in the same, so this idea of the semi-infinite limit is very nice, but this limit we can have something, we quite usually obtain something new, for example, some central extension. And that's why this limit requires some care. And technically, our logic is the following. So we want to have in the limit the full toroidal algebra, but practically we take either one half or another half or third half, some sense rotated bottom half. This line is orthogonal to the right line which corresponds to Heisenberg. And it appears that right side converges, but only analytically, if you want, under certain assumption Q and V. By word analytic, I don't mean anything deep. I mean that in the limit, so if we take this algebra, action of this algebra here for finite n, we get finite geometric, it is given by finite geometric series. And if n goes to infinity, we have to sum infinite geometric series, and the sums converge under this assumption. If we take this assumption, then we can take analytic continuation. So this we take analytic continuation in both of these cases, and obtain the action will be given by rational functions. But a priori sense, we don't know how these algebras will commute. So here for this half, we say that this converge on this assumption. So every relation is preserved. Then we take analytic continuation. Every relation is preserved. So okay, similar for this subalgebra. But we don't know. We know nothing about their relationship, because we take different analytic continuations. If you want, they take convergence on the different assumptions. And in order to glue these two subalgebras, we actually use the bottom subalgebra, which converge always, because it appears that in certain formulas, this algebra is given by finite sums. Wonderful. And then our logic is the following: that we can glue this to this, we can glue this to this also, and we can also show that the representation is unique. So everything can be glued. The fact that the limit of the toroidal algebra is taken by some parts, this is quite natural. Actually, in the paper by Schiff and Vasirovich, I mentioned one of the very first slides, also limit is taken by certain parts independently, and then it's linked. They're good. Anyway, this is how we did. So I'm not sure that this is the best way, this is the only way, but at least this approach worked. Okay. Now I'm almost done. You see, I have numbered my slides. So this slide number 16. That this is not for me. This is not the end of the story, almost in any sense. So there are many questions. So depends on what do you prefer. So probably Roma prefers the question about what is geometric meaning of all these constructions, of these vertex operators. Maybe it has some relations to the proof by Konov-Smirnov using 3D mirror symmetry. But I cannot say much about this. Another question is we didn't prove actually Gorski-Nego conjecture because we do not prove window condition. And of course, we expect that this window condition should follow from some facts on the finite level, where we have finite number of variables and non-symmetric polynomials in them. And but this is to be done. And in terms of integrable system, the main question is the duality. What is a, so we have action of two algebras, but usually such stories leads to the identification of certain integrable system from one of dual realization of the integrable system. And in some spirit, it is known what should we expect from this GLM case, some integral systems due to Lukyanov and Katausov, but this is not done, and this may be an interesting question to study. Anyway, so there's no question, so I don't know what to talk about. So I prefer to stop. Thank you for everybody who came to the attention, and then whatever you want.
Thank you.
Thank you very much. Yeah. Any questions? Not so. So thank you, Misha. And we're.
Thank you for coming.
Yeah. So we resume in half an hour. For